All right, let's find the sum of 7/9 and 5/6. We know that we can't combine these because we don't have the same pieces. So what size piece should we make so that we can compare them and use the same? Well, we learned from the last example that we can multiply both of our numerators and our denominators by the same number, and it is still an equivalent fraction. Just as a side note, that students are going to be practicing this over a long period of time, so they will naturally deduce the quote-unquote rule for how to make equivalent fractions on their own through many different examples that they're working through. So I know we're going through this quickly, but we are covering grade 5 in 3 weeks, where you have an entire year to cover grade 5 standards. So keep that in mind. I know that 9 times 2 is 18. Similarly, 6 times 3 is also 18. So our piece sizes would be the same. So I'll take 7 times 2 and 9 times 2, and 5 times 3 and 6 times 3. So we end up with 14 copies of 1/18 plus 15 copies of 1/18 for a total of 29 copies of 1/18. Yes, this is an improper fraction. However, let students be flexible with the way that they represent numbers. Remember, we say this is 29 copies of 1/18. We could say that this is 18 copies of 1/18 plus 11 copies of 1/18 for one whole and 11 copies of 18th, since we surpassed the unit mark by decomposing our numbers. Let's add 1/3 and 2/5 using an area model. So I have a unit box. Doesn't matter what size that box is, just that it's a unit box. And I've split it into thirds. I want 1 copy of 1/3. I also have another unit box the same size as the thirds, except this one is cut into fifths. And I need to shade 2 copies of 1/5. By having one unit going horizontally and the other vertically, we have created a 3 by 5 rectangle. So notice along the left is 3 units, or 3, and along the top is separated into 5. So if I create an equivalent unit fraction, still cut into thirds, and have the first row highlighted for 1 copy of 1/3, and I do the same with my fifths, I see that altogether that I have 5/15 plus 6/15 for a total of 11 copies of 15. Using an area model is an extremely powerful model for the following reasons. It can be used to add or subtract any fractions or fractional quantities. It uses fractional equivalence, a common unit, and the same whole number thinking that we've used in the past. It parallels the steps in the standard algorithm for addition and subtraction by finding a common denominator. It is a powerful pictorial stage between the concrete and the symbolic stages. Let's add 3/4 plus 4/5 using an area model. So I have a unit box cut into 4 pieces. I want 3 copies of 1/4. I have the same size box, except this one is cut vertically into 5 pieces, and I want 4 copies of 1/5. By having one unit going horizontal and the other vertical, we have created a 4 by 5 rectangle. So the same amount is shaded. Now only I have 15 of the 20 shaded to represent 3/4, and I have 16 out of the 20 shaded to create the 4/5. So 15/20 plus 16/20 is 31/20. Now we can do to show that this is 1 unit. Note that each one of these boxes represents 1 unit. I created above another unit box. I shaded in the yellow, and I started moving my blue pieces to fill up one whole unit and then the other box just using partial. So I see that we are able to fill in one whole unit plus a partial other unit, 11 out of the 20. Understanding the procedures of rational number computation is a prerequisite to success in algebra. We should make use of explicit properties of operations that explain the exact computational process we are accomplishing with fractions and decimals. Let's ask why 5 copies of 1/9 plus 2 copies of 1/9 is equivalent to 7 copies of 1/9. It is because we break it down, decompose 5 times its unit fraction plus 2 times its unit fraction. Then we can grab the 5 and the 2 and multiply it by 1/9 since that is the common factor. Add our whole number pieces. So that 7 copies of 1/9 we know is 7/9. So we decompose the fractions into unit A copies of 1 over B. We use the distributive property to undo the common factor which was distributed. We added the whole numbers together. Homework. Read the problem and observe the student's model and answer. If you agree with the problem representation and answer, explain why. If you disagree, construct viable arguments that could help the student better understand the problem and see his or her mistakes. Sarah wants to make a jam recipe that calls for 1 quart of grapes. She has 1/2 of 1 quart of grapes and 2/3 of another quart. Does she have enough grapes? Explain. Here is Sarah's model. Sarah says that she needs more grapes to make 1 quart. Scan and upload your response to the grape jam discussion board. Respond to one of your classmates' responses. Homework. Using the whole numbers 1 through 10 at most each one time, fill in the boxes so that the sum is equal to 1 whole. Start over. Can you do this another way too? Justify both your solutions by using a model of your choice. Scan and upload your solution to the Make One discussion board. Check out what your classmates discovered. The photo that you're looking for will be in the discussion board. I know it's not listed here, but the photo that you're going to fill in the boxes with are in the discussion board, so make sure you check there. Let's review some meanings of multiplication and division. So multiplication could mean that we're adding equal groups, and division could mean equal or fair sharing. It's called the partitive concept. Further equal grouping or segmenting is the quotative measurement or repeated subtraction concept. Multiplication and division can be represented by increasing or reducing quantities, as well as moving from factors to products or products to factors. We can make numbers smaller by multiplying them by fractions less than 1. Use a number line to show that when we multiply 3/4 times 2, our product will be smaller than 2. We want to think of this as 2 copies of 3/4. So here's 1 copy of 3/4 plus another copy of 3/4, which brings me to 6 copies of 1/4. Which is the same as 1 2/4 or 1 1/2. Again, be flexible with the way you allow students to represent their numbers. Let's use a tape diagram to show that 2/3 of 15. We think what is 2/3 of 15? So I have a bar strip or a tape diagram here that's split into 15 equal pieces. I'm going to break them down into thirds so that I have 3 groups of 1/3. I'm particularly interested in how many 2/3 is. So I then get to count. 2/3 is equal to 10. individual squares. Ashley needs a rope for the tug of war that would be 1 3/4 times longer than the 12 feet of rope she has. Show the mathematical expression you would use to find the new length. Use a number line to show Ashley how you figured it out. So we could think of this as 1 3/4 times 12, or 12 times 1 3/4. So I have a number line. I'm going to choose to do an open number line. So the first option is taking 1 3/4 times 12. So I want 12 copies of 1 3/4. So I will continue 1 3/4 making copies of it until I reach 12 of them. So I know that 12 times 1 3/4 is equal to taking 12 times 1, the whole, and 12 times 3 copies of 1/4. And 12 times 1 is 12. 12 times 3 is 36 times 1/4. 12 plus 36 copies of 1/4 is the same as 9, so 21. We could also think of this as 1 3/4 of 12. One group of 12 is 12, and 3/4 of 12 is, so I'm going to let the entire tape diagram represent 12. I want to split it into 4 different groups. We need to know how many are in each group. Well, 3 would need to be in each group to build to 12. I particularly want 3 of them. So 3/4 of 12 is 9. So we knew that one group of 12 is 12, and 3/4 of 12 is 9, so 12 plus 9 is 21. Use a number line to show which product is smaller, 5/8 of 16 or 3/4 of 16. So I have a number line, and I have the number line built up to 20, but we only need 16. So when I look at 5/8 of 16, I broke down the entire tape into eighths. I want 5 of them eighths, which is equivalent to 10. I broke down my 16 using a tape diagram into fourths, and I want 3 of them fourths, which is 12. So I can see that although 5/8 appears to be larger because we have larger numbers, it's not always the case. So 3/4 of 16 is greater than 5/8 of 16. Multiplication can be used to scale down. Let's use an array model to show the product of 2/3 and 3/4. So I have my model going vertically and horizontally. I have it broken to thirds and fourths. I want 2 copies of 1/3 and 3 copies of 1/4. What I'm going to do is overlay them on top of one another so that I get the same unit except it's broken to thirds, a 3x4. Notice that the color which is overlaid is their actual product. So we now have 12ths, and 6 of the 12ths are overlapped and shaded. So 6/12 is also the same as 1/2. This is a great stepping stone. As students work more with this model, they will be able to generalize the relationships between the numerator and the denominator. Naturally, students will be able to generate the rule itself, that when we multiply two fractions, we multiply straight across.